Okay, so hello again to everyone, data experts, data enthusiasts, and anyone else tuning in. As you may see from this very first slide, today we will be talking a lot about neural networks. But before we get into all of that fun stuff and wizardry, I would like to begin with some introductory words. The case we are discussing tonight is the Ontotext case, Look, I Am Your Father, and you will be hearing more about Team A's solution. So you might be wondering who Team A is, and there is a very short answer. It is an A team. It was in fact formed in the data chat that we are currently using for the presentation. So I urge you to use it. It's an awesome place. More about our team. We are 6 people, and actually a rather diverse team. As you can see, we have people from countries ranging from Belgium, Spain, Greece, and of course Bulgaria. So my teammates are here on the screen. You can see Vinesh, Radoslav, George, Ruben, and Kuzman. I am Anna, and I will be presenting for you tonight. I would also like to stress that some of my teammates are currently in the chat. So if you have any questions, you may address them towards my teammates. So without any further ado, let's move forward. We actually thought a lot about what we could present to you today, and we decided to show you not only our results, but also the process we went through, the steps that we took, and the twists and the turns that we had. So all of this begins with the data at first glance. And here is what we had to work with. Actually, what you see before you right now is what we had before the datathon started. So this was information made available by Ontotext for all teams who were deciding what case to choose. Basically, the problem boils down to this. We had to improve the search experience of clients working with annotated text and to bring more efficiency to them. So to understand this, we need to look at the structure of the data. As you can see, we have company 1 and company 2, and what we are looking at is actually their relationship. This is shown here in this parent column, and it is a sort of flag column. It shows you whether company 2 is a subsidiary of company 1. So whether company 2 is the daughter of company 1. And actually, we have some information in the form of article excerpts in another column, which is named a text snippet. And our task was all about building a model that can guess this relationship based on certain text that we have in the text snippet column. So this is what we had to do. As you can imagine, we had an action plan from the very start. And a summarized version of that action plan is here in 4 points. Firstly, data exploration and pre-processing, seeing any particular things about the data, anything that we need to address at the beginning. Then we wanted to do something extra that could potentially improve our results in the final models, and of course, the models. So we have classical machine learning techniques and neural networks. And you will hear more about all of this in order. So let's move on to data exploration, which was the first more important step. So we begin with some basic statistics. The number of parent companies, which was 440, subsidiaries 447, and the number of unique words 39,535. All of this is very basic. It doesn't really give you any useful information about the data. So let's look at something more valuable. Here you get more info. So we have the number of total observations, which was about 90,000. We actually discovered that we had around 10,000 duplicates. So what we did was to discard those for further analysis. And by this point, something on this slide should be screaming at you, and it is this blue graph that slightly resembles a Pac-Man. It actually shows you something pretty important about our data, and it is that the data is very imbalanced. I talked earlier about the relationships. Company 2 could either be a subsidiary of company 1 or not. So when it isn't, we have a negative relationship, and in 70% of cases, this is what happens in our data, and in 30% we have a positive relationship. Now, this, as you can imagine, has some implications for any further steps when we do pre-processing or modeling. And this is not something scary. We just have to bear it in mind when we do anything else. So now that you've seen this, try to remember this Pac-Man graph, because I will be referring a lot to it later on. Now, by this point, you have a slight idea about our data, and probably we should move on with our ideas as to how to do proper pre-processing. So, as I mentioned before, we wanted to do a little something extra. And very often when we are faced with a data problem, it is a good approach to find more data. So we can do that either externally or do some engineering and do this artificially. One way to do this is to augment our data set. And in natural language processing, this is done via natural language generation. And this has several forms, for example, back translation or paraphrasing, article spinning. All of those methods allow for additional text snippets. If you remember this column that we had with the text excerpts, those are our text snippets. We just needed to create more in the training set so that we could potentially have better results at the end. The basic idea is to maintain the conceptual relationship between the companies and not to have the same semantic structure, to introduce some diversity so that our models can better detect relationships. And all of this should happen without any dependence on specific words. So this is the general idea behind this data augmentation. And in fact, we did a lot here. And I would like to make a shout out to Ruben, who is in the chat room. He's the one who spent the most time pursuing this task. So if you find this interesting, you should write to him. He can explain a lot more about it. But the few things that we did was to implement several article spinning APIs, to set up a function to perform back translation. And what we ended up using finally was a free service, a website, which does exactly that. It spins the text and gets the results that we wanted. Now, as you can imagine, during the Datathon weekend, we actually faced certain limitations in terms of time, in terms of technical issues. So actually, we had to restart this process. We had to split our data into smaller chunks. And in the end, we did not manage to finish this. Another thing we wanted to do here was to include co-reference resolution as an additional feature. Now, this basically means to use words such as they, it, its, and other similar ones, and to replace them with the respective company names. What this would do is to allow our model to detect relationships not only based on the companies as mentioned in the original snippets, but also based on references elsewhere in the text. So again, adding more depth to any model that we may develop. And having said all of that, I would like to say also that our team loved these ideas. We are all huge fans of those. Unfortunately, they did not make it into our models. So the results that you see are not based on this augmentation. Unfortunately, it was never finished. So bear this in mind for the results. And here on this slide, you may see just our basic ideas for someone who might have more time to develop this task, what they could implement. Right, so we have covered this now. You know what we wanted to do with the data, but we haven't yet shown you what we actually did. So let us fix that and show you the pre-processing that did happen. So here, what you can see is firstly the issues that we encountered. We saw that some words got concatenated with entity names. If you imagine a company name, let's say Google, in some instances we would have random words stacked to that word. So we needed to fix that, and we added spaces to each known company. Another problem that we faced, and was slightly more complicated, was overfitting on company names. So we wanted to avoid our models learning to detect just the organization entities without getting the context. So what we decided to do was to introduce aliases for the companies with constant strings. This means that within the text snippets, the companies will be represented with the aliases company 1 and company 2. This means also that the model doesn't learn the exact names of the organizations and will preserve the order of the relation. So this is one crucial thing that went into all of our later models. Another thing we saw was that some organizations are not presented in the snippet. So actually, we saw 200 instances of snippets where we have only one company mentioned from the respective pair. With these, we decided to actually discard them when calculating the distance feature in the classical machine learning models. Right, so what you see on your right is the split we introduced to the data. We split it into a train set, a validation set, and a test set. And one thing I would like to stress here is that we maintain that ratio that you saw at the Pac-Man graph often. So we maintain the relationship of 70% negative relationships and 30% positive ones. That is something that is crucial if we want to get decent results and not a jumble of things. So now you know the basic things that we did to our data. Let's move on to the fun stuff, to the modeling itself. What you see here are two main things. Firstly, classical machine learning, and secondly, neural networks. When it comes to neural networks, we actually had two different approaches and two different logic as to what goes into the neural networks and respectively what comes out. And here again, a shout out to our neural network engineers who are Radoslav and Vinesh. They basically introduced those elements and made the models special. So without any further ado, let's look at the machine learning techniques. I would like to remind you here that our problem was a natural language processing one. And when we have something like that, we have TF-IDF. We did apply TF-IDF along with logistic regression, support vector machines, and naive Bayes. Unfortunately, with naive Bayes, we got very poor results. So we are not including it in tonight's presentation. But let us take a look at what we get from the models that work well. Firstly, TF-IDF with logistic regression. We trained the model with default parameters on the training set, and we are actually going to be looking at F1 scores. One bracket here, you will be seeing a lot of F1 scores. You will not see probabilities, and the reason for that is that in this way, the ratio of negative to positive responses does not have such a significant effect as in the accuracy metric. So this is what you will be seeing us talk about when we speak of evaluation. Right, so firstly, default parameters, you can see the F1 score firstly on the train set and then on the validation set. And on these confusion matrices, I would like to bring your attention to these two positions. So at the 0, 0 position, what we have is the true negatives. So when company 2 is not a subsidiary of company 1. And at the 1, 1 position, we have the true positives. So when company 2 is a subsidiary of company 1, this will persist throughout our models. So what happens when we introduce the hyperparameter optimization is that the F1 score, of course, rises. Here it is, roughly 0.567. And again, the true negatives and the true positives. And the final test is performed on the test split that we had from earlier. Again, it slightly rises to 0.578. Now, this is the summary for TF-IDF with logistic regression. We have something quite similar for TF-IDF with support vector machines. The support vector machines that we used were linear. In terms of results, here we go. The first F1 score on the training split is quite low. You can see the confusion matrices and respectively this reflection of the Pacman graph, if you'd like to put it that way. We have a very low score. Then we introduce hyperparameter optimization, and it goes to nearly 0.60, as you can see from the confusion matrices as well. And finally, we test it on the test split. Here we go again with the result. Before I go further, I would like to also make a shout out to George, also in the chat room. He's someone who spent a lot of time tuning those hyperparameters. So if that is something which you're interested in, you may ask questions to George. And now is the time that we get to the more interesting things, the neural networks. We will begin with long short-term memory and some CNN. But before you see the network, let's introduce some principles and considerations. Now, I told you that our two architectures differ mainly in terms of what goes into the networks. So in this first model, what happens is that we take each pair of companies and the various snippets that go with them, and we introduce them to the network separately. If you want to hear it in a simpler way, we basically take the separate rows and feed them to the network separately. This is basically how we feed it. I mentioned also earlier that we are encoding company names. So within those text snippets, all of the excerpts, we have no company names. We have the aliases, company 1 and company 2. Having that in mind, we can move on to the model itself. So this is our initial model. Here you can see our F1 score. It is 0.788, and this is the initial one. A few more words about this network. It is a bidirectional LSTM. We use some dense layers and, of course, word embeddings. And before I get more into that, I will show you what happens when we add some CNN filters. The main effect is that we get more true positives and less true negatives. And here again, I can remind you about that imbalance in our original data. You can see it reflected again. The F1 score is 0.598. Then more details looked at word embeddings. We actually tried several word embeddings. Firstly, Keras embedding, and secondly, pre-trained word embeddings with GLAV, where every word has a semantic meaning as well. And basically, when we feed all of this to the network, it spews out some classification, what we actually see here. If you're more interested about this technical stuff, you can read more about it in our article. But now we can see some of the output that we get from this network. Here is how it looks. We have the companies, and what you might notice here is the effect of the way that we fed the neural network. So you might see that these companies, for example, AT&T and Time Warner, which are a pair, appear 3 times. So we have them once, a second time, and a third time. This is something normal for the way this network was set up. This is because we have the network evaluating the different text snippets that are related to this specific pair. If you see here their respective numbers, they are different, and this is the peculiarity about this model. And this is also one of the crucial things which makes this model different from the next one, which brings me to it. It is our architecture number 2, the attentive recurrent neural network. Now, in terms of principles and considerations, we have a few differences. If in the previous network we fed the model specific text snippets associated with different pairs, here we are introducing grouping of snippets based on those unique company pairs. You might be wondering why we would do that. And that is because for each pair of companies, there are numerous text snippets. If you imagine, for example, Google and YouTube, there are thousands of snippets about such companies. If you imagine smaller companies, there might be 2 to 3 to 4 snippets about them. But only some of the snippets actually reveal the parent-subsidiary relationship. So what grouping allows us to do is to actually determine which text snippets reveal this parent-subsidiary relationship. This is why we introduce this as another type of logic. One thing that we maintain is the encoding of company names. So that would be company 1 and company 2 as aliases entered into the network. You can see actually here one big effect of this methodology. We have a reduction in the number of relationship rows from 79,000 to basically 950. I mentioned earlier that there is some variance in the number of snippets, and the example with popular companies and less popular companies makes this pretty clear. Now, some more rules that will actually make this crystal clear, I think, the basis of what we are doing. So a snippet in our case is the text excerpt which we have in our text snippet column. And we take each snippet and equate it to a sentence. Even if grammatically in a snippet you have several sentences, for our purposes we call it a sentence. Then we consider all sentences for a pair. If we run with the Google and YouTube example, this means that we take all of the snippets for Google and YouTube, and we consider them basically as one single document. What this means is that at the end of it all, we're looking at document classification for the different company pairs. Now, all of these here are some more technical stuff. For example, recurrent neural networks on TensorFlow need sequences of equal length, which is why sequences are adjusted, either padded or truncated. But what is probably more important here to mention is that we had to split our data again, because this transformation greatly reduced the number of rows that we're working with. And again, here we have the reflection of the Pacman graph, the ratio of 70 to 30% negative to positive relationships. So it is reflected here. Now I'm going to show you a very brainy slide. It has a lot of explanation of how all of this works in practice, but I think it would be much more useful for you to take a look at the graph that explains it in a more clear way. So we have a few things here. Let's begin simply. We mentioned earlier that we take company pairs and make documents from all of the sentences, all of the snippets about them. Here, this is just an excerpt of that. Here we have 2 sentences about Google and YouTube. This is the first one, and this is the second one. And what we do is that we feed them to the network. So every word becomes a vector and is fed into a gated recurrent unit. What actually happens after that is that these words are concatenated and inputted into the unit. Then this unit outputs a vector in the case of each word. So this happens right here. We have this word attention. What happens at this step is quite crucial. We have the attention network, which learns the weights from these vectors, and then outputs attention network in a sentence vector. This is over here. Then what happens is that these sentence vectors are combined into a document vector. At this other level, the sentence attention. What you should pay attention to here are the weights. So the model, the attention network, actually learns the weights. So if you look at a vector such as acquired, you can imagine that it is more important when we consider parent-subsidiary relationship. Whereas in this second sentence, we have no such word, and you can see that we have less importance associated with these weights. This is basically how this whole model works. It is nothing complicated, but it is rather different from our previous model. Another thing that this model allows for is that we can later on actually find out which are the important sentences that trigger the prediction. This is also something different. If we had to look at the output, again, we have the 2 companies. This is the potential parent company and subsidiary company. What you will not see here, as compared to the previous model, is any repetition of these company pairs. And this is because we concatenated all of the text associated with them. Again, this is the main difference between our two approaches. Otherwise, you get a probability for company 2 being a subsidiary of company 1. That logic is the same as before. Right. So by now, you have seen our architectures, the model we have applied throughout the dataton, but our work actually did not end here. We have some more models developed after the dataton. They were developed by Radosław and are building upon the LSTM approach. So in terms of principles and considerations, a few things have changed. We have a few additional layers. A new feature is included. It is all about organizations' positions. And in terms of data preprocessing, we are basically maintaining most of what we did so far. About the two models, here is the first one. Again, what we're doing differently is that we are passing company pairs explicitly to the neural network. You can see the model in terms of layers on this slide, but I would like to focus on the results. So what happens is that we are training on the train and def split, and we are validating against the test split. You can see here our F1 score, 0.829, sorry. And again, you can see the reflection of the Pacman graph because we have the true negatives here and the true positive over here to the right. Another thing we do is to test this on the test set that we later get from Ontotext. Here we have a result of 0.118. The second model has one additional layer, which allows it to capture more complex features. And in terms of results, when we look at the results on our test split, so this is a test split that we got from our original data that you saw the previous graphs for. We have a score of 0.825. This is slightly lower than the one from the previous model. And when we test it on the test set from Ontotext, we get a 0.126, which is slightly higher than what we had in model 1. Now, this is actually the best performing model of what we developed. And it also concludes the results that I am going to be showing you tonight. Actually, we covered quite a lot. We covered our process. We took a look at the data, what we wanted to do, what we actually did, what models and architectures we applied, and their results. In terms of conclusions, I suppose we could sum them up in a few ideas, such as starting prepared always pays off. It is very important to be ready to experiment until the very end, because you never know what you're going to discover. Also, don't forget to have fun and enjoy the process. Another thing which may sound trivial, but remember that teamwork makes the dream work. And finally, one weekend is not enough, but it is definitely a decent start, and you can learn a lot. We would also like to thank the amazing people behind the dataton, as well as Ontotext, mainly for lighting us with the sprightly and lively spirit to conquer not only the data challenge, but the sleepless weekend as well. And before I end the presentation, I would like to bring you back to the beginning, because we started this whole journey with a Star Wars quote, and our team united behind the idea that we could finish on one as well. So here it goes, and it reads, well, if Joyce could think, there'd be none of us here, would there? We leave the interpretation to you, and with this, on behalf of TMA, I would like to thank you for your attention. And if you have any questions, we will be happy to answer. That's all.
Thank you, Annie, for the incredible presentation. It was really, really interesting to hear the approaches you used, and also how you solved this interesting task given by Ontotext. I'm asking Chris if there are any questions.
There is one in the chat.
There is one question in
All right.
chat. And Yeah.
Well, I don't think we discussed this about the Star Wars quote with Ontotext. We talked more about the data with them, if that is the question you had in mind.
Thank you, Martin, for the question. If you have any further questions, this is the time to share them. Yeah. Okay, cool. So we are expecting the next question.
Okay. I should probably mention that in terms of more technical questions, my teammates will be better equipped to answer. So can you inform as well?
Okay, if they want to join us, of course, they're welcome, because I see Ruben here. And by the way, I want to tell everyone, the audience, that Team A was one of the most dedicated to the challenge, as they almost didn't sleep during the challenge, during the datathon, and it was really funny how they was awake during these 48 hours, but succeed in the mission of reaching the finals. So yeah, congrats. So okay, probably there are no questions left. I want to thank you again for the presentation. Of course, it will be uploaded on our YouTube channel, and also will be shared with the people in data chat. So again, I will suggest everyone, and also encourage you to follow our channels, because it is really important not to miss such interesting presentations, and also to be really involved before someone presenting in their article. And you can also firstly check the team's articles, and also write your questions below the articles. And of course, you already know that we are another challenge coming at the end of April, and it will be interesting for all of you who are students and want to participate and want to try another data set with cryptocurrency data. So yeah, see you in the data chat. This was from us. And thank you really, Annie and A-Team, for the great work you did. And yeah, see you soon. Bye.
Bye-bye. Thank you.
Bye, guys.